start with the next talk in this session. It will be on material and process selection for circularity. Essentially, it's extension of the yesterday's talk by Professor Reddy, and we will be discussing about the technologies which help in enhancing circularity. So it will be given by Professor Chiyam.
Thank you. Good morning once again, all of you. So I think I will be continuing the discussion, but look at it in a different facet on what are the material and process selection for circularity. In this, probably I will be emphasizing more on the technologies which are enabling it. So I think Professor Reddy was focusing more on the materials part of it and the product selection part of it. So I will focus more on the technologies which are enabling such possible integration, etc. So usually there are various technologies you can think of which are commonly used in the context of remanufacturing, etc., additive manufacturing, cold spray, hybrid technologies. But I think I will not go into this format. Okay. So rather, what is interest for us is the context, our circular manufacturing context. So whether it is reducing the material wastage or to reuse or refurbish the components, how you can repair the components, repurpose and also recycle. So what I will be doing in this session is kind of talking these objectives of our circular manufacturing in the context of different technologies. Okay. So what are the various applications and what are the various technologies which facilitate it. Okay, so there are a lot of possibilities there. So briefly I will be talking about the integration, each of it from an example point of view or an illustration point of view. What are the technologies possible for facilitating circular manufacturing applications, etc. So why these? Essentially, so these are examples I have taken from the work which was happening with the Sirman. So all of them are presented in the eco-design previous instance. So I will be taking examples from work presented and carried out just to give a specific context to the applications. Okay. So let's do one by one mapping. So firstly, let us look at how you can reduce the material usage. So usually when you mean reduce, of course there are various ways of it. So, but one way to look at it is, can you reduce the material wastage and both increase the efficiency of it, and also many times, so it's not always possible for you to increase the efficiency of the process. The process itself has probably a certain upper limit, best possible scenario. So we also need to look at how you can hybridize different processes so that you can leverage the advantages of different. So one such example, what we have taken is the hybridization of deposition and deformation processes. So usually additive, if you look at it, so typically is deformation. So imagine something like this, an object like this is a shape you want. Typically what happens in a additive manufacturing, if you directly do it through additive manufacturing, you need to then remove the base plate, machine the surface, etc. Okay. So there is a lot of, because by definition the additive manufacturing is layer by layer from this. Okay. So what happens is, although you can achieve this object using additive manufacturing, there is a lot more material removal, machining which will be required to get the final shape, because you have to scoop out the material from the bottom, the support material, etc. Okay. So the question is, for example, can you use other applications? So for example, like deformation processes. So instead of using a flat substrate, can I use a kind of deformed substrate, a formed substrate, and then do deposition on top of it? So what I am doing here is actually mixing judiciously two combinations or two processes. One is your additive manufacturing, the other is your deformation processes, and by doing a combination hybrid of these, I am able to get better finish and final object. Also, I am able to reduce the material wastage involved in the process. Okay, so this is one such example where you can actually get better material usage, reduce the material wastage by hybridizing two processes. Okay, now that's the thought process, but that's not always easy. What is the challenge here is, of course, so what we are doing here is kind of integrating it with the sustainability. Okay, so how do you break what is the process planning is one part of it. Okay, and similarly, for example, if you also have some small features, some small repairs, even those can be easily carried out. Okay, but the bigger challenge here is most of our processes are fine-tuned for layer by layer deposition. So the moment we call additive manufacturing, it is always layer by layer which first comes to our mind. Whereas in this context, we are doing not necessarily flat layers, but even inclined and non-conformal deposition also. So here whatever you are depositing need not be a flat surface, can be an inclined surface, can be a curved surface. Okay, so the challenge which comes here is how do you then deposit it for a curved surface. So just we are taking a simple illustration. So imagine the tool path you are taking. Okay, so whether you are going and doing the infill in this manner for a simple curved path or in this manner. Okay, so what happens here is when you are doing it like this, the material flow is assisted by the gravity, and you can see that although you have done the deposition, there is a higher accumulation of metal at the bottom than at the side. Okay, whereas for example, if you start from the center and go on like this, okay, then it has a better distribution of the material, a better retaining of the material on curved paths. So the major point here is layered manufacturing in flat surfaces is kind of fairly established and well understood. But the moment you want to do layered manufacturing in curved surfaces, deposition on non-planar surfaces, then the challenges are a lot more. Okay, but it is, so this is some work which we are also engaged in doing. So the idea here is, but by doing so you can increase the efficiency of the process. Okay, as I said, so in step 1 you can take a simple plate, deform the substrate to the nearest possible using forming processes like incremental forming, etc., and then use that non-planar substrate for the deposition. Okay, so this is one example where hybridization of the process can help increase the efficiency of the process, overall material usage, wastage, etc. Okay, also the other aspect is how you can improve the efficiency of the process by using digital twins. So this is the powder bed example. So if you also properly plan, then your material, your thermal stresses, your material support mechanism. So here we have essentially, for example, we are trying to reduce not the part usage but the support mechanism. Okay, so how you can reduce the support mechanism or the material wasted in support mechanism also by using different strategies, by digital twin, etc. Okay, and so that is one example of the first case where you are reducing the material wastage. The next one is how you can refurbish components or reuse some of them. So one example of it is, for example, let us say you have a shaft, okay, and it is worn out. Okay, so what do you do with such? It is a very common problem. Many times your aerospace, different flight components, shafts, etc. have this problem. Okay, they are subjected to wear and tear. Okay, after multiple usage. So the problem is, it is intact, it is working fine, but you need to increase the thickness of it. Okay, so one such method is essentially, typically there are versions of it. Some of them are cold spray, some of them are thermal spray. Okay, so the idea here is in cold spray, the plastic deformation is more significant. In thermal spray, the material melting is more significant. Okay, but ideally, either way, you can selectively continuously add material. So what is happening here is, you can see this is the material gun, okay, which is spraying a thin liquid, and then this shaft is rotating, okay, and you can essentially resurface the shaft, increase the thickness of the shaft, etc., by continuously depositing a thin layer. So you are not selectively doing it, you are uniformly addressing the material thickness, the wear of the shaft in multiple places. Okay, so in such situations, what happens is you are able to again increase the life of the component, the shaft, etc., without having to replace it. Okay. So the third example or application we have is in the context of repair. Okay. So I think refurbishment and repair are almost like overlap with each other. There is no specific demarcation what qualifies as refurbishment, what qualifies as repair. Okay. But roughly, if you look at repair applications, so additive manufacturing is one of the common ways in which you do repair applications. So typically, for example, we use mostly DED based applications. So what are the various metal additive applications? At least powder bed and DED, direct energy deposition. Okay, how many are aware of powder bed and DED? Okay, okay. So is there anyone who does not understand DED versus powder bed, etc.? Okay. So additive manufacturing, there are common techniques. There are multiple techniques, but the most common of them are powder bed and DED. Okay, but not all of them are suitable for repair applications. Why? Because if you take powder bed, for example, you are putting powder into it, you are kind of then spreading a thin layer of metal powder, and then there is a blade. So what happens is, repair applications in powder bed are very difficult. It's not that it is impossible, but most of it is very difficult because the whole process assumes that you are spreading a thin layer of powder, and where a blade will be able to move and spread the powder in an uninterrupted manner. That's not always the case in most applications, whereas DED, on the other hand, is usually more convenient. You can selectively add material where you are required. So what happens is, DED applications are ideally suited for repair applications in the additive manufacturing segment. So for example, this is what happens. Okay, so this is kind of your typical steps you see. So for example, there is a small damaged part, you can see the dent there. Okay, so firstly what you do, you take the component, okay, you clean it up, polish it, so that there are no other impurities. Because what will happen is, if there are impurities, the other material you are depositing will easily peel off. Okay, so have you seen road repair done? Okay, so usually you see, essentially, if rainy season comes and the roads are damaged, okay, they don't just bring the tar and put it there. Why? Because the whole tar will just remove. There is enough dust, etc. So they consciously even sometimes damage the further also, so that whatever is the material being added, kind of fixes there is not easy. Okay, so typically, so polishing, cleaning, etc. is part of the preparatory steps which are there for repair. Okay, then what you do, you clad the material in a selective manner. So for example, you see here, you have added the material, and then you finish, you do the finishing operations, etc., and finally you have the component which is repaired. Okay, so such applications, additive manufacturing, DED, etc., is ideally useful. Okay, so this is typically the process which happens. Okay, so you have the digitization, then the restoration, and then the post inspection, etc. But the major challenges here is essentially, one, the material composition and the analysis technique. So because when you take a component, okay, you are not always sure what is the material composition. Okay, it may be manufactured by some other product, maybe a different manufacturer. Okay, so you should know exactly what is the right material composition and what is the right combination of material to be added. Okay, so that's the first challenge. Okay, so you need to get the material right and you need to get the metallurgy right. Okay, so there one thing which helps here is essentially kind of the standardization. Okay, so if there is some certain form of standardization available in the processes, in the materials you are using, if there are not too many variants but a specific basket or specific family of components, it easy to establish the process. Okay, you don't have to reinvent or set up the process every time. Okay, the second challenge is typically the computer-aided CAM or manufacturing, flexible manufacturing parts, etc. Okay, so here the most, for example, let us say you are doing, I mentioned about additive manufacturing, depositing, etc. But typically the codes available for additive manufacturing are mostly for complete deposition. That means you have a part, okay, and the complete part you are doing in a layer by layer manner. Such automated CAM tools, such automated tool path manufacturing, etc. is easily available. The problem is, if you only want to do certain part of it, okay, if you want to repair, the tool path generation becomes a bigger challenge. Okay, so there are established proven tool path generation is not, I mean, at least it's not standardized yet. Okay, so one is essentially kind of you require to the tool path required for it. Okay, two, even if you are able to generate the tool path, you have to also worry about the collision more importantly. Okay, tool collision with the remaining parts. Whereas in a normal manufacturing, you are not too worried about tool collisions because you are always going up in the jet. In this case, what happens is when you bring repair applications, you have to worry about the tool path. You also have to worry about the collision detection for the tool paths to avoid with the other parts, etc. Okay, so these are important. So, and the challenge here is this has to be done is unique for every component. Every repair application will have a separate set of requirements, will have a separate set of, so automated tool path planning, typically what is available in part production, etc., is not easily applicable, extendable here, and a lot of manual expertise and a specific domain expertise is needed. Okay, the third challenge is essentially kind of the material and the structural property analysis after you deposit. Okay, so it's, even if you take the material, the outcome of it also depends on not just the material but the thermal history, the temperature, deposit temperature, etc. of the components also. So every component you have to worry about the material, you have to worry about the tool path, but you also have to worry about what is the heat accumulation, what is the thermal kind of history or the thermal situation at each of the component. Then if there is excessive heating generation, HAZ generation generated there, it may again lead to a different properties or different behavior. Okay, so that is other challenge you have to keep in mind. Okay, of course, post machining planning. So because most additive manufacturing processes are near net objects, you don't get net shaping in most processes, so you need to do some finishing operation also in addition to the machining. So again, if it is uniform, it's easy for you to plan the machining operations, but it is only for a region. The post finishing operations also are little more complex. Okay, and then finally the post inspection and in situ monitoring. So usually what happens is you are always designing the component together, and you know some random points or some fixed points to check for integrity, check for strength, or check for homogeneity, etc. Here what is happening is you are not looking at the complete component, you are looking at a specific part of a complete component. So there the steps, what to expect, what to look for, okay, again needs to be standardized. Okay, so these are typically, so although why repair in general is possible in additive manufacturing, you don't see them very often or very commonly adaptable, is because there are many challenges in it's not that they are impossible, okay, they can be addressed, but these challenges persist when you are talking about repair of repair of components using additive manufacturing. Okay, of course cost is also another factor. So here what happens is the cost of it always increases. So the major cost is not the process, the major cost is the expertise. If you are using a factory setup, a kind of a line, assembly line, etc., production line, assembly line, the expertise required out of the worker is not very significantly high, because all the planning and steps are established, okay, and the worker only needs to execute it. Whereas here what happens is, because there are no established planning, the expertise of the operator required in these applications is much higher. Okay, so you can't just afford with a normal operator, you have to have a very experienced expert operator handling these situations. Okay, so again that another, usually that is the cost component which comes into it. Okay, so there is a possibility, but it has a long way to go. Okay, so that's the reason, one of the reasons why it is not universally seen, why it is only seen in one or two applications, not very kind of commonly available. Okay, so these are a specific set of challenges which you have to encounter. Okay, the next one, next example is how you can repurpose for different applications. So I'll take the example, two examples. First example is reconfigurable tooling. So here what happens is, imagine you are doing some forming operations. Okay, so typically forming operations may need a specific die or a specific component specific die for manufacturing it, stamping dies for example. Okay, so and all these dies have to be made, has to be kind of, there is a big investment to be made, etc. Okay, but these days the number of components is reducing. So for example, if you are manufacturing some 10,000 stampings, some 20,000 stamping, it makes sense. But if you are looking at only 3 components, 5 components, okay, so there a dedicated tooling, etc., may not be very efficient way of doing it. So you are also looking at essentially, for example, how you can think of reconfigurable tooling, where the tool is made up of multiple pins. Okay, so what happens is there is no single this thing. Okay, so there are multiple pins which are being reconfigured, positioned according to the requirement. Okay, and then they help act as the support mechanism, act as the bottom substrate, etc., for different forming applications, stretching applications, etc. Okay, so in many applications reconfigurable tooling can be used. So in fact, I mean, so the same concept for reconfigurable tooling, reconfigurable jigs and fixtures. Okay, so the attachments needed in fabrication of the components. Okay, so these kind of tooling which you are using also should be flexible and generic instead of specific applications. Okay, similarly the other part of it is repurposing not just of the tools and fixtures, but even the machines itself. Okay, so for example, imagine you are talking about product reuse. Okay, you are talking about part reuse, okay, and you're talking about material reuse. So all that we have seen, okay. But there is one big important thing, machines, okay. How do you reuse machines also? The problem today is the technologies are continuously evolving, okay. Whereas, so before the machine gets damaged, the machine is becoming redundant in most of the applications, okay. So that is true with components also. That's also true with machines, for example, okay. So whenever you talk about product reuse, part reuse, etc., can you also think essentially how to address the machine reuse, the machine kind of repurposing, etc., okay. So typically that word we use is we use the word retrofitment, okay, so that you bring in new applications, new advantages or these things for the old component, okay. So for example, I think so the idea here is can you bring in even digital attributes for an existing machine. So for example, if you're talking about industry 4.0, does it mean that you have to buy a separate new set of machines, new set of welding machines, CNC machines, etc., or can you enhance the capabilities of your existing machines to these applications, to these requirements, okay. The latter is preferred, okay, because there is a significant capital cost involved with the machines and you don't want to kind of completely remove them and put new placement. It takes a significant effort, okay. Whereas if you can increase the capabilities of the existing machines, okay, it becomes much more advantageous, okay. So one such example is what we have done is for retrofitting of our CNC and welding deposition edit. So I mean essentially CNC machine is converted into a metal additive manufacturing system also, okay. So that is some work we have done some long back, okay, at least 15 years back. So the advantage here is you are looking at a older system, a 3-axis system, which you can also use it as a additive system as well as a removal system. So the same machine becomes additive and subtractive are possible in the same setup, okay. So if you look at essentially a typical metal additive manufacturing system, you have energy source, you have the raw material supply, you have the kinematic movement and the software for tool generation, okay. So these are the various aspects, activities related to the deposition which is happening there. So typically the energy source and the raw material are what you use, for example, from a weld deposition system or a laser deposition system, etc., okay. And the location control and the software you can leverage the CNC. So essentially what happens is, if you look at cost wise also, okay, the footprint of the kinematic setup, the linear guides, the x-axis, y-axis, etc., is significant, okay. At least it takes 50 to 70% of the cost in any metal additive manufacturing system is typically taken up by the kinematic systems, the movement of the laser head or the movement of the welding head, okay. So if you can use standard existing machines, standard existing options at your disposal, then it becomes much easier. So that's what we have done in our case, okay. So the software of course is generic, okay. So what we have done is integrated the CNC machine with a welding system, okay. So firstly integration of the physical integration. So what we have done, this is our CNC machine in our lab, okay. So we have identified where are the stress bearing elements, etc., okay, and then mounted the welding torch next to it, okay. So kind of where if you move the x-axis or the y-axis or z-axis, the welding torch also moves, not just the machining head, okay. So that's the simple physical integration, okay. But the physical integration is the easiest part of it. The more difficult part of it is I cannot have a x-axis, y-axis controlled by the machine and the welding controlled separately, okay. I cannot say that look go a circle, okay, and then look at, I run the G code from the controller, okay, and then have the welding separately operated, and whenever the point comes, I switch on the welding and then it slows, then again I look at it, switch off the welding. It's not feasible, okay. So physical integration is fine, but electronic integration is also important. You have to control both these together, okay. You have to control the position, XY position of the welding gun. You also have to control the on and off or the other parameters also using the same interface. Now that becomes a difficulty, see, because whenever the CNC system is typically not designed for you to mount welding system, etc. Okay, so how do you get over such challenges? So one thing what we have done is, this is essentially how we have loaded it, etc. Okay, one thing for the electrical integration what we have done is, what are the things which are available in a CNC which you don't use using welding, using deposition? Typically coolant, okay. So you put the coolant for machining, okay. So whenever you are doing machining, you kind of use your M08, M09 commands for coolant supply. Now, can we repurpose the same codes for the welding? So that means whenever I am running my code, M08, instead of switching on the coolant supply, will be able to switch on my welding supply, okay. And similarly M09 will switch off, okay. So what we have done is simple, just a toggle switch you have added to the CNC setup, okay, where the toggle will be able to select between the machining mode and the deposition mode, okay. So if I want to operate the machine in the deposition mode, that also can be automated, we didn't bother doing it, okay. But let us say if you want to operate the machine in the machining mode, okay, then your M08, M09 goes to the coolant output and you have your coolant running. If you want to operate it in the additive mode, your same M08, M09 command will switch on or switch off your welding unit, not the coolant unit, okay. So what we have also could do is, without any changes to the CNC, the electrical unit, etc., in the same existing set of things, you can also control, so the XYZ and the welding, all of them are controlled using a single G code command, okay. So the same G code command controls the welding setup, controls the positional setup also, okay. So this is some simple integration we have done, okay. I mean, again, it's not a big deal. The point here is, you can do such integration by using the basic elements of the machine itself. So most elements allow you to do, yes.
So it's quite a, like from a technical perspective, why do we have to like figure out so many things?
Correct.
The easy way, which I think is, we can use reverse engineering process.
Okay.
While we assembling any CNC machine or any kind of, because when we are assembling a machine, we know each and every component.
Correct.
And if that is fed into the software, application software, and then by using a digital image processing, you know each and every component.
Correct.
And if something happens wrong, when you overuse the machine, so some part is crippled or some part is, what should we say, बहुत ज़्यादा घिस गया है.
Okay.
So now the detector is there.
Correct.
And from digital image processing, the detector is able to analyze which component is affected component.
Okay.
And then this CNC machine will run.
Okay.
And instead of figuring out what should be repaired, what should be done, it will pinpoint with that particular defective part.
See, that is generally true in bigger machines or in what we call as arrayed components where they are fixed, etc. Okay, but imagine if you have a specific component with a repair. So usually there are two kinds of damages which happen. One, predictable this thing which happened because of wear and tear. Okay, so you have a regular this thing. Other ones are which are you cannot exactly predict, and you cannot. So, for example, it's small breakage. Okay, so if you are using a gear or a pulley system, so yes, the pulley system will be worn out is predictable. Okay, and you can know when to maintain, then you can have a maintenance schedule of replacing it, etc. Or you can have a sensor which looks at it. Okay, but imagine sometimes you are using a gear system. Okay, and where let us say I'm in a gear system for cutting trees. Okay, so there you don't know what is the forces you are encountering. So sometimes the gear may just break, one of the teeth of the gear may break. There it is not predictable, and this essentially what you need is where you cannot predict, you cannot monitor always. If you are able to monitor, well and good, there is no doubt. Okay, but what happens is, at least if you look at it in a factory, 80% of the machines are not easy to monitor regularly. Okay, so that is the reason why where you cannot monitor, these systems come into the picture. Where you can monitor, definitely. So for example, what we are looking is two scenarios. What are the machines and design paradigms you will do for the future? Okay, if I am designing a machine additive manufacturing system or a machining system today, I will then keep these concepts in mind and design it. What is my other problem is, I already have a machine in my head setup from last 20 years. I can't get rid of it. I can't buy a new one. Okay, these are the things to bridge. Okay, new generation machines, there is no problem. You can, you're correct. Okay, so you can integrate all the sensors into it and you can get a rail. The problem is making the old generation machines work in a new generation context. Okay, so there it becomes challenging. Okay, so here what we are looking is actually, can I use a CNC machine? Actually, the CNC machine who used was a discarded machine from Taiwan. They used it for 30 years, SAS machine. They stopped using it. Okay, then we purchased it. Okay, so why? Because the machine comes at 1/4 of the cost. Okay, so the cost of it is significantly low. Whereas if I have to invest, so how can I best extend the machine which is existing? That is the question here. Okay, so there it is kind of, I mean, the technology of the machine is unfortunately 30 years old. It does not have any of the sensors. So these situations, these become inevitable. Okay, so I think so the point here is definitely when you are looking at design of next generation machines, these are the concepts you need to keep in mind. But when you are also are kind of handling and are inevitably this thing with legacy systems, old generation systems, then you have to find ways to integrate them and at least enhance their capabilities to a certain extent. Okay, so that's kind of what we are doing. So the idea here is you don't want to touch the controller. You want to have the same Fanuc controller. Okay, the reason is essentially, for example, if you are so the machines are also standard like your products. If I have a let us say a M6 nut bolt, 2 rupees it costs. Okay, maybe 4 rupees. Okay, but if I want a M6.5, a very 6.25, a specific category, it becomes very costly. Okay, it may cost you 200 rupees. So similarly, a standard Fanuc controller for a CNC is mass manufactured and will come around 50,000. Okay, whereas if you have a custom made controller, it usually 10 times more. Okay, so you have a lot of cost advantage by the standardization of the machines available, and you want to leverage that. Okay.
I just want to ask, is there any technology right now available? So yes, I accept the fact that we have, very older machines available, and refurbishing them is a better option rather than be putting up a new setup.
Correct.
Can we scan, do a scan of these machines to understand which part has which mobility or which component is used for what? So that when we are into the process of repairing them, at least we know the functionality of the older machines.
That is correct. That is available. That application is available. So most of it, of course, it may not happen automatically, but that know-how is available. Okay. So see, the point is there are two things: repair. I'll come back. Okay. Repair and repurpose. Okay, my machine is working. I have to repurpose it for my different application. So the problem is not where the problem is in the machine. The problem is the product itself has changed. Okay, so then I am not repairing the machine. I am repurposing the machine. The machine works fine. I have to repurpose it for a different application. Okay, so that is where the challenge comes. Okay, yes.
So I would be able to add a new code to the list of codes available. Was it a memory issue or was there some sort of or was the format not?
So essentially, for example, that is correct. Okay, so when we added a new machine, we had just simply some extra relays added. Okay, and we were some 52, 53 they gave, and we were able to use it. Okay. In the older machine, we did not see. These are typically at the time of manufacturing. If you have, it becomes easy. Okay, at the time of if you later add them, it is possible, but it is very costly. Okay, or sometimes it is. So usually the PLC circuit algorithm is made in an integral manner. So the moment they are making the machine, the PLC circuits are decided. So if you add them at that auxiliary additions, you can have. But sometimes you cannot go back in the past and modify them. Then these are alternative methods. If you have auxiliary, that's the best way. If you don't have auxiliary, the point here is you are not dependent. So what I'm trying to demonstrate here is, if you have the machine designed originally for auxiliary applications, etc., it is fine. It is safe. But even when your machine is designed for some other purpose, most of the machines have adequate redundancies which you can use like this. Okay, so what you are looking at is, can I use some of the inbuilt machine redundancies for different applications? Okay, so that is essentially the idea here. Okay, so the repurposing, etc., always is there. Okay, so the other point you have to also remember. So for example, it's other example you can think of is, so I was discussing some yesterday with a drone startup. Okay, so their task is simple. So actually the problem here, what they are doing is, most of the drones you look at are only allowed in visible line of sight. Okay, out of sight or out of line of sight are not allowed. Okay, but if you want to allow it, what are the protocols you are going to use? Okay, you can think of GPS, you can think of radars, etc. Okay, but that is again a new investment, a new big these things. Okay, so for example, and they were actually looking at some existing radio frequencies which are no longer being used. Okay, so for example, they were looking at ham radios. Okay, so is it necessary to do ham radio only? Not necessary, but the advantage there is that bandwidth is already available and has become redundant and no longer applicable. Can you use those frequencies, these things, repurpose it for the drone? It makes it easy. Why? Because essentially you don't have to again reinvent newer chips, newer frequency modules for those. Okay, all you are doing is, you have an existing factory, you have an existing manufacturing facility, you have an existing capability and know-how to manufacture, for example, ham radio frequencies. You are repurposing it. Okay, so the question is, can I use different technology? Can I use different wavelength? Yes, but that wavelength has become redundant and I am repurposing it. Okay, so similarly the effort here is, the machine is working but the purpose is gone. Okay, can I repurpose it? Okay, so that's kind of what we are looking at. Okay, so if I go back, okay, so essentially, can I have advanced capability in the existing machinery? Okay, so that's my basic premise here. Okay, so so what we have done is, okay, so integrated the electronics, etc. Again, as I said, in the newer machines we didn't have to do all this trouble right in the beginning. So we have two different machines. One was an old 20-year-old machine. So we had to undergo all this trouble. When we then had a second machine, and there we were aware of all these details. So right in the beginning itself, we ordered extra relays, extra additional these things, where we didn't have to even do this coolant trouble, etc. Okay, if you are able to design from the right beginning, it's fine. Even if situations where it is not possible to do, this is just to demonstrate that most machines have enough buffers, okay, which you can reuse. So of course tool path, etc., that's a different, okay, so I will not go into the tool path here. But again, why I am demonstrating here, again we did not have any other tool path. Whatever is meant for polymer 3D printer, you can bring it in the G code and make enough modifications, where the existing, for example, slick 3R interfaces can be used even for weld part depositions with the necessary changes, okay. So these are a few examples, okay. So some of the components we have built using this setup, okay. So the advantage is both finishing and deposition are possible in the same setup. So I can make the component, I can also do the finish machining of the component in the same place, okay. So I did not create a new machine. I had a machining system which I have repurposed it, enhanced its capability to do both machining and deposition, okay. So that's kind of an example of how you can repurpose objects, particularly machines, capital intensive items, etc., okay, for different applications. Because the product requirements are changing very rapidly. The machines typically run for 20 years, 30 years, but the product is becoming obsolete much quicker, okay. So that's okay. And the last example is the example of recycling, okay. So for example, how can you recycle components? A particular advantage or a particular context comes from disjoining objects, okay. So for example, if you use multi-material joining, most applications, for example, your automobiles, etc., have aluminum, copper, aluminum, iron, or titanium, etc., multiple joints, okay. If you have different components, it is okay. You can easily segregate them. But what happens is, in such multi-material components, disjoining becomes very difficult, okay. So some of the materials which use multi-material, okay. So for example, people use either roll forming. So this is essentially roll forming. So they take the two rolls, then join the material together, and there is a small metallurgical bond which is formed. Other process is typically your friction stir welding, where you are able to mix the two objects, and again, I mean mix, or there are other methods, for example your rotating pin, etc., okay. So the way you are able to join multiple materials, and you have different applications for it. The challenge comes is when you want to recycle them, okay. So the same multi-material becomes a difficulty or challenge for you, because material segregation becomes difficult, okay. So essentially, so if you look at how you can think of disjoining multiple materials. So typically what people have done is looked at the fracture strain mechanism to break the component, okay. So what they do is typically introduce the fracture strain at the multi-material intermetallic interface, okay, and then help segregate the components. So typically where it is to be done, where the force or fracture has to be applied, again has to be seen. So for example, typically what happens is you have three kinds of fractures. One, fracture in the joint due to lack of metallic bonding, okay. So you have enough, so this is the soft material, this is the hard material, the white and the black, okay. And you have kind of gaps here because of insufficient bonding. So typically roll bonding, for example, happens here, okay. So roll bonding, sometimes the air gets entrapped, okay, other forms. So this bonding is not sufficient. So in such situations, it's kind of easy to apply the force and then delaminate them, break them, etc. In other applications, you also have a intermetallic layer which is formed, okay, which also has a strong interface, okay. So again, how you apply the load there, okay. And some cases you have a intermetallic but much thicker. So where, for example, like your friction stir welding, where the materials are being fused also, okay, so they are mixed together. So their intermetallic is born, and intermetallic is much thicker also. But mostly what happens, this intermetallic layer is also typically brittle in nature. Okay, so what kind of, pardon?
Easy break.
Yes, correct. Okay, so essentially that will refer, that kind of will define what kind of a fracture strain you are able to imply, okay, and break. Okay, so these are kind of some examples how you can disassemble the components which you are making. Okay, so this is various forms, various aspects you have looked. Okay, but the general example is there are different possible potential applications or processes for circular manufacturing. Okay, I have just picked few examples from the work various collaborators etc. are engaged as examples. Okay, there are a lot more possibilities, lot more processes. What is important is what is the orientation purpose you are looking at. Okay, so essentially as long as you are purposing them with the application. Okay, so you can look at different refurbishment or reuse. Okay, so different. So if sometimes you have to repurpose a machine, sometimes you have to repair an application. Okay, so as long as there are different such contexts, okay, you have to also choose the applications and the technologies suitably for different applications. Okay, so this is just, I mean, one example each I have picked to demonstrate what are the possible ways of doing it. Okay, so fine, I think I'll stop here. If there are any questions, I'll be happy. Yes.
You said
Sit.
additive manufacturing technologies are used for repair applications.
Correct.
Only metal alloys can be used for additive manufacturing, or composite materials also can be used for repair applications?
Composites also can be used. Definitely, there is no. Okay, so usually, sit. Okay, see, the challenge here is the integration. Okay, so when you are using metal itself, even when the metal you are melting and putting it in place, you have issues of continuity, you have issues of this thing. That become even more complex when you are doing a composite figure. Okay, because the composite typically you have a layers, fiber layers, etc. So they have to be integrated. Okay, so integrated them also becomes much difficult. So yes, as a possibility, but not easy as a actual case. Okay, but it is possible. I mean, it is definitely possible for composite applications also.
I have a cutting tool, sir. I use it for machining, and the tool where as well. So I want to repair that cutting tool. Basically, it's a tungsten carbide cobalt cutting tool. If I want to repair, which additive manufacturing technology can I use? Laser power fusion or laser dye?
I believe DED may be more suitable. Generally, also DED may be more suitable because DED gives you lot more control parameters. Okay, you can control that spot size, you can control the material rate, you can control the heat affected zone, etc. So the number of control variables at your disposal are much higher in the DED process than in the powder bed. A powder bed, you have to kind of spread the layer. First you have to spread a 40 micron layer, then you have to fuse it into a 12 micron or a 10 micron powder. So there you have to be able to, even geometry has to allow you to spread. Okay, so those challenges come in when you are using powder bed. In certain applications, definitely powder bed also may be, but very limited geometries powder bed can allow repair. DED is more flexible, more options, so usually it has more control variables. More control variables means difficult to operate, but also can adjust in very complex situations also. Okay.
Are there any studies of in situ monitoring of repair applications?
In situ monitoring of repair application.
Manufacturing technologies.
Oh yes, yes. Okay, so in fact our own group, Dr. Gopinath does in situ this thing. So what we do here is essentially, as I was saying, what is the challenge in the repair applications is the metallurgical condition. Okay, so is the material homogeneous? Is it proper happening? So typically what we do is look at the deposition, deposit the material, capture the deposited weld pool using IR camera and pyrometer, link it with a closed loop control of the laser power. Okay, so what then happens is your laser power is increasing or decreasing, ensuring that the deposited molten pool is of same consistent temperature whatever you have set. Okay, so it is possible. So that way your material homogeneity, ensuring material homogeneity becomes easier. Okay, it is possible. Okay. Okay, all right. I think then we will close this session. Thank you.
Okay. Yeah, thank you, Professor Surya, for the talk. So then we'll break now for lunch, and then again we'll meet in the after.